video for Facebook.
I don't know why I don't.
Video for Facebook.
I don't know why I don't.
Okay, we are live. Hello, everybody. Welcome to another exciting episode of Sidewalk Science. We have our most of our regular panelists here today. Dr. Ivan Phillips has some family visiting this weekend, and he's got some other obligations, so he won't be able to join us. But we've got our anatomist and biologist, Abby Hafer. We've got particle physicist, Michael Albro. Hi, Mike. We've got astrophysicist, John Doty. And we have science educator, and critical thinking teacher, Joanne Reed, Dr. Joanne Reed. So welcome to our panelists, and welcome to those of you who are viewing us live. Today, we have a program that some of you might find reminiscent of some information you've seen previously. There was a PBS special about this topic, or a related topic, in a famous book that was released a few years ago. And the topic for today will be about Tiktaalik, which is a lobed finned fish. But before we get into that, let's spend a little bit of time talking about some recent science news. So it looks like, Joanne, you're sharing your screen. Can you wait to do that just for a few minutes until we get through some science news?
Just messing around and screw things up, I think.
That's okay. No harm, no foul.
Lots of harm, lots of fouls, and now I don't know how to undo what I've done. Okay, I'm gonna do that.
There you go.
Hi.
All right, so some science news. There's one piece that I'll bring up first, and that is news about a amazing new discovery of a white dwarf star. So a white dwarf star is the core of a sun-like star that has exhausted its nuclear fuel and continues to collapse in on itself after the heat of nuclear fusion has abated. And it turns into a very, very dense ball of material, degenerate electron matter. And typically, if you hear about if you hear about white dwarf stars, you will hear about them being about the size of the planet Earth. Well, recently there was an announcement that some astronomers believe they've identified a white dwarf star that is about the size of the moon. So quite a bit smaller than the planet Earth, but paradoxically much heavier than a typical white dwarf. So white dwarf stars get smaller as they gain mass. And at some point, they become so massive that they go through a kind of a phase change. It's a bit of an oversimplification to say that they get more massive. Stars that are more massive leave behind something that's even denser than a white dwarf, and that's called a neutron star. But this amazing piece of news about a moon-sized white dwarf is pretty exciting. It kind of puts new limits on what scientists had previously thought could become a stable white dwarf kind of stellar remnant. So I thought that was pretty exciting. Do any of you have any insights or thoughts about that news story? No?
The physicists.
Well, the interesting thing is that Jupiter is about the largest body you can have that isn't supported by heating it up. If you were to add mass to Jupiter, it would get smaller. And a white dwarf is an extreme example of that. So yes, It's on the side of the mass radius diagram, where if you don't have nuclear fusion going, the more mass you have, the smaller the thing is. And the interesting thing is that we didn't really think that anything could get quite that small without collapsing into a neutron star. But at the ragged edge of stability, we don't understand what goes on very well.
Yeah, it's sort of different sorts of degenerate matter that are very difficult to fabricate in earthbound laboratories, and so understanding their the states, what kind of crystalline or liquid states or whatnot that they might exhibit is really challenging, as I understand it.
Yeah, anything that isn't held up by thermal pressure is degenerate matter. The Earth is degenerate matter, but it's not like a white dwarf in that what is producing the binding of the electrons isn't external pressure, but it's the electrostatic attraction of the nuclei in the rocks. And so when you have matter that is subject to sort of normal chemistry and petrology and all that, the more you pile onto a planet, the bigger it gets. When you get as big as Jupiter, now down in the core of Jupiter, the matter is nothing like a rock. It's metallic hydrogen. The electrons are freely moving and not really bound into atoms at all. And as you pile more and more stuff into a body, more and more of the body gets to be like that, until you get to a white dwarf where most of it is being held up by this electron degeneracy pressure, which has nothing to do really with the attraction of the nuclei for the electrons, but is because of the exclusion principle.
Yeah, a quantum mechanical effect.
It's a quantum mechanical limit. Well, the Earth is the same in the sense that the pressure inside the individual atoms is very high, but and then as you get outside the atoms, there's still this quantum mechanical force that keeps the atoms apart and keeps you from falling into the core of the Earth. But when you get to when you get to Jupiter, you're reaching the point where that atomic pressure is not very important, and when you get to a white dwarf, that atomic pressure is negligible.
And it's
so
nuclear.
It's just all the pressure of gravity that's pushing the thing down. And if
John,
it's yeah,
I have a question. So, what is the source of energy for the white dwarf? It's radiating energy. What's the source? Is it nuclear or is it gravitational or what?
it's predominantly just that it was born hot and it's slowly losing that heat because it was the core of a star.
That's 26 million degrees, yeah, or thereabouts.
So it is not. It's just radiating away its internal heat. It's not actually generating more heat.
Nope.
If it was still collapsing, that would give heat. But so nuclear reactions are not contributing. You see. Okay.
Right.
Nuclear reactions are not contributing. That's even true of Jupiter. Jupiter radiates several times as much.
A white dwarf. Jupiter doesn't radiate heat like a white dwarf does. A white dwarf is white hot.
Yes,
right?
but Jupiter radiates several times as much heat as it receives from the sun. So most of the heat that comes off Jupiter is heat from its formation.
Yeah, it's still cooling down.
It's still cooling down.
Billions of years later.
Now, it's not as hot as a white dwarf. It's quite cold, but still, it is mostly its internal heat is what it's radiating.
And interestingly, the Earth still has some of that leftover heat from its formation as well. I've read that about half of the heat of the guts of the Earth is due to cooling off from its initial formation, and the other half is due to energy released from radioactive materials, uranium and whatnot, that's trapped in Earth's core and mantle. So the Earth is also cooling off.
Yeah, but it is radiating, as you say, radioactive. Radioactivity is contributing to the Earth's heat,
Right.
to keeping the center of the Earth's hot, and that must be true in Jupiter as well. But it's not a typical nuclear reaction.
Yeah, it's a fission
But-
reaction rather than a
Yeah,
fusion.
it's a very small contributor to the Earth's thermal balance, and it's also a small contributor to Jupiter's thermal balance. It's really primordial heat that is producing Jupiter's
Thermal.
infrared radiation.
All right, let's move on to other science stories from this week. Do any of you have any science news articles that caught your fancy that you want to spend a couple minutes talking about? I did see another one. Recently I saw, there are these famous chalk figures in Great Britain that are carved on hillsides and whatnot. And there's one of a naked man that's fairly famous.
And very obviously a man.
Longman at Wilmington, I've seen these, several of them, yeah.
Yeah.
They're thousands of years old.
Yes, this particular naked man has a very prominent male part.
Organism.
Yes, organ. And in any case, scientists have studied this particular chalk figure, and using sort of fluorescence kind of dating, where they can see when material was last exposed to sunlight and perhaps, I don't know this for certain, but maybe something like cosmic rays, when it was irradiated and exposed on the surface, they can see when this material was last exposed. So they dig down to the lowest level of the scraped away chalk to see when it was last exposed to the air or to radiation from the sky, and they found that it was this chalk nude male was carved sometime around 500 to 1000 AD. So they put a nice date range on that. Interestingly enough, in the same article, they talked about a very famous horse. There's a horse figure carved into the side of a hill.
Yeah.
And this horse, they use things like snail shells. So apparently, when the Romans invaded Britain, they liked escargot. And so they brought in an invasive species of snail that sort of got loosed, like life will tend to do. And experts, or an expert in snail physiology, looked at the snail shells that existed in the soil, both below where the chalk had been excavated and the channel around the chalk drawing had been excavated, and also some soil that had impinged on some of the chalk and been cleared away. So they went through various stages of analyzing the pieces of snail shell left within and around this chalk drawing, and determined that the horse, the famous horse chalk drawing, dates from about 3,000 years ago. So we have the nude man from 1,000 years ago, give or take, and the horse from about 3,000 years ago. And I just thought it was really delightful how these different scientific methods that are relatively modern or incredibly innovative in the case of the snail shell fragments can help us solve some of these ancient mysteries about archaeological things.
Well, the mystery is not how they were made, so, because the chalk is only not very deep under the turf, but why they did it. I mean, is it to show the gods, messages to the gods, or just for fun?
Right. Well, the article did talk about at least the nude male chalk figure. There's a temple, and I'm sorry, I forget the term. Viewers and people who watch this video later can look this up, but apparently there was a local pagan god that has a temple right near where this male figure was carved into the hillside, and this temple is believed to be associated with trying to convert the pagans in that area from worship of this god to worship of a Christian pantheon or Christian gods and saints. And the speculation, pure speculation, no archaeological or other kinds of hard evidence about it, but the speculation is that this figure carved into the hill was to get people's attention and say, hey, if you worship this god, maybe this is a figurine or a figure of supposed to represent this this pagan god. If you like this pagan god, come to our church because we've got, you know, good news for you, etc. So appropriation of a lot of pagan holidays and pagan pantheons is really common in the Christian church. You look at the association between different saints and how they correlate to pagan deities. The Virgin Mary correlates to some pagan earth goddess mythologies, etc. So this cultural appropriation of religious figures is something that early Christianity did a lot of, and maybe this nude male chalk drawing and its associated nearby temple was evidence of that kind of thing happening. So really just interesting stuff. All right, so we're about 15 or 20 minutes in. Let's go ahead and have Joanne talk to us about this, one of the most famous fossils that has ever been discovered, and how in the world it's relevant to you and me and maybe some other creatures as well. So Joanne, you want to take it away?
Sure. First, I want to apologize to Abby. This is really your area of expertise, and I don't mean to steal it from you, but I do remember the wonderful line you had a few years ago about this is a fish in a tree. So after I get through with this, I'll let the real expert talk about it. Now, I'm going to try and share my screen. I've never done this before, so this is going to be fraught with danger.
That works.
Now, what do I have here? Is everyone can see this? Is this all
Good.
right?
It's fine. Yeah.
So if I were to scale through it, you can see it fine?
Yeah, so we see about 4/5 of it. The very bottom of your slide is cut off a little bit, but
So what I'll do is I'll do a sort of a thingy like this and a thingy like that. Whoops, I don't want to do that.
Go to full screen.
Is that all right? I'm at full screen now?
No.
yeah,
The only thing I can do beyond this is slideshow.
Go to slideshow, full screen.
Now, if I go to slideshow, it's going to blank me out. Oh, no, that's all right.
Good. Yeah.
yeah, that looks
That's
great.
That's fine.
Perfect.
So, it all starts with an interesting question that everyone has asked for centuries. That is, if we look at the skeletons of all land animals, all of us, they're the same. And we keep asking why, because it doesn't make any sense. Why is the skeleton of a frog and of a lizard and of a human and of a bird and of all the other animals essentially the same? And this has just bothered the heck out of people. That is, if I take a look at horses and cows and pigs and donkeys, and I take a look at skeletons of different kinds of animals, I see great similarities. So for instance, here's a frog, which is of course an amphibian. There's a dinosaur, which of course is some kind of an interesting old reptile. Down the bottom right is a lizard, which is a reptile. Up the upper right is a bird, and down at the lower left is a cat. And if I look at this structure, I see something that is remarkable. That is, we all have the same body plan. Now, let's start with the spinal cord, because of course that's us, that's where chordates. And so we have a long spinal column, and up the front, and we know it's the front because that's where all the sensory organs are. Sensory organs lead to the mouth. The mouth is the beginning of the alimentary canal. That's where food comes in, and we follow all the way down to the other end, and that's where the remnants of food go out. We see a long, wonderful spinal column, which connects everything together. There's a beautiful head up there. We see ribs, which contain the body, which contain the torso, and contain essentially ribs and heart and things like that. We go to the front, we see beautiful, right there, beautiful scapula. That is the strong bony connection between the skeleton itself and the forearms. Then we see a heavy pelvis and great looking legs and a great tail. All of us have it. And this just shouldn't be. Why should all the animals in the world look like this, essentially? And we can get into even greater details when we look at the legs. If I look at the legs of all of animals, I see an interesting combination of bones. I see one bone coming from the body itself, going to two bones, going to many, going to five. 1, 2, many, 5. That's a basic plan for all life on land. And again, it doesn't simply make sense. Why should this be true? If I look at amphibians, now amphibians go back, what, 420 million years, 360 million years? These are the first animals that could live outside of the water full time. Now they went back to the water to breed and that kind of thing. But yes, and we see, look at this, 1, 2, 5, and they're right in there, many. And there's a thumb sticking in here, so it sticks right out there. If I go one step further and I take a look at dinosaurs, now this goes back 250 million years, and we see again 1, 2, many, 3. Oops, 3. What's going on with 3? Well, if we look at the skeleton very carefully, we see vestigial fingers up into the wrist area here. We've lost, and so what's happened is the functionality has gone away, and these 3 fingers have remained fully useful. And in fact, in this case, this is the grasping things, and you can see that this particular foot is a very dangerous type of thing. And so they're there, they physically exist, but they're no longer useful, so they've grown back. And we see this quite a lot, for instance, in modern birds. And if we take a look at apes, including ourselves, we've only been around for, apes and stuff have been around for 60 million years or so. And again, the same kind of construction. 1, 2, many, 5. 1, 2, many, 5. Look, 1, 2, many, 5. 1, 2, many, 5. We just continue all of this time from before the dinosaurs all the way to the present day. What's going on? Why do we have this? And if we look across species, again, we see the human. Here's the humerus in the human, and in the bird, and in the bat. And the radius in the ulna, and the phalanges, and the metacarpals, and the carpals, and the metacarpals, and the phalanges. And we've got them all. They're all the same, it's just the proportions are different. And here, again, here you can see in the chicken, there's the thumb. Right there, that little bitty thing. So when you're eating your buffalo chicken wings, there's the thumbs, and it's way up there. So it's just a vestigial piece now. So the question is unresolved. It was unresolved for centuries, millennia. Why do all land animals have a similar to skeleton? The question, of course, then resolves, and we said, could we have inherited it? That is, what came before mammals and birds and dinosaurs and lizards and amphibians? Well, fish. Now I look at a fish and I see a totally different skeletal plan. I see a backbone which runs down the middle of the body. It's not along the top where everybody else is. This is in the middle of the body. Look at the huge number of ribs. And these sure aren't capable of walking. There's no neck. This is not this ain't. And also look at the geometry of the body. The geometry of the body is tall and narrow. Whereas we look at our bodies and the bodies of others, we're flat from front to back and wide, so that we have a nice resting position. If you lay on the floor, you're in a totally relaxed position. You can stay that way. If you lie on your back, totally relaxed position. You're in a position of stable equilibrium. If you lay this fish on the floor, it'll flop over. And so we need something, we need to think about something that's flatter. And so we look at this modern fish and we say, no, that's not the answer. And then we remember something important. That's a modern fish. That's 250, 350, 450 million years after the first fish. So what did the first fish look like? Well, let's take a look. We thought, oh, see, that's what I said. We thought that this particular fish was extinct. And then we found out, again, 20, 30 years ago, that the people in the Indian Ocean areas were catching these things all the time. This is the coelacanth. This fish has been around for 450 million years. It's amazing. It's essentially unchanged. We have skeletons of it going back to that, and we actually have live fish. Now, this is not a tiny little fish. This is about 2 meters long, about 6.5 feet in length. They're a big fish. They live to be about 100 years old. Now, look at this, these huge fins. This is a much flatter body. Not completely flat, but a much flatter body. We see these huge, powerful fins, and if we take a look at them, we see 1, 2, many, 5. We see the beginnings of a pelvis. Oh, are we getting in the right direction? Well, possibly. Again, if I look here, here's the front arm, if you will. There's the upper bone in the arm. There's the dual lower bones. There's the phalanges. There's the pelvis coming down here. We're going, all right, we're getting in the right direction. Now, this is still a fish. This is not going to walk on land. This is going to flop over. So we need to think about something that's sort of like this, but it's flatter. And then what kind of an area would we find something like this? We would find this in the estuaries, in the marshes, in the shallows. We need a fish that goes into the shallows to hunt, to just look around, and maybe just poke its head out of the ground every once in a while, just for a goodie that might be lying there. And so, back in 2004, Ed Daschler, Neil Shubin, and Ferris Jenkins went looking for this particular kind of animal. And they went to Ellesmere Island, which is way up here. This is the northernmost island in all of Canada, immediately off the coast of Greenland. And the reason they went there is because this land has been scraped away. When the glaciers came through, it just scraped away hundreds of millions of years of topsoil, leaving stuff behind. Now, we've looked through these areas before and found that these are going back a long, long way. And they said, let's look at some area where we're looking for something that's about 375 million years old. And there's right here in Ellesmere Island, we found it. And we say, all right, let's look, see what we can find. And that's what they found. This is named large freshwater fish. And in the native language, it's Tiktaalik. And I am told that you would pronounce all the letters. So this double A is it's a wonderful glottal stop. So for all of us in Massachusetts who pronounce beer, and a glottal stop, or have a bottle of beer, this is beautiful. It's Tiktaalik. So large freshwater fish, notice the head. Flat. It's a flat head. Notice where the eyes are. Notice that you've got a nice body plan. You can see legs and stuff. And go, all right, let's take a really close look at this particular thing and the skeletal remains that go with it. Here's the actual head right here in comparison with what we think it looked like. And again, this is a reasonable drawing of it being partially in and partially out of the water. You can see eyes on the top of the head. So it can go in the shallows, have its eyes, just like an alligator or a crocodile can today. They can cruise along in the water, they can look above the water, they can look below the water, and they can see what's going on. They can climb up onto the land. Again, notice this is a big fish. This is 2.7 meters long. That's nearly 10 feet. So this is a huge critter. Notice the way we've drawn it here. It's actually pushing up. So it's got arms out in front. They can lift the torso and lift the head. Critical. If we look at the bone structure of these four, we see exactly what's going on. Notice in your own arm, if you were lying on the floor and you were trying to crawl, how would you move? You'd extend your arms upwards and then you'd push down. You'd push down with this upper arm. So you get a lot of pressure down to lift your body off the ground so that you could move it back. And we can see right here the musculature allows it. There's the big scapula, there's the arm bones, and so it's able to push down very, very well. Now, as you're going through this push, the position of your hands has to change. So physically, you have to be able to rotate your hand both this way and that way. And again, this bone structure allows it to do that. Your radius and your ulna allow this kind of movement in your hand, and your wrist allows this kind of movement. So as the arm's going down, you lift out and you move forward. Then you do it again and again, very much like a modern reptile does. And now this creature has that ability. The first creature that we've ever found that has the capacity to push down, lift its body up, and then move along and be able to repeat this time and time again. So we could look at this structure very carefully and say, what's going on here? And we have the three stages. Here we have an ancient fish, again, but big fins. And we see that it has relatively lovely pectoral fins. Now, notice there's the humerus, there's the radius, there's the ulna, here's the intermedium, here are the radials, and the digits. Now, we go from this fish to Tiktaalik. Notice we've got a much larger humerus, radius, transitionals. There's a beautiful, beautiful area here of your intermedium and your radials and your digits. And finally, coming to Acanthostega, which of course is a full-grown land animal. And again, it's the same kind of thing. We're moving from the direction of a swimming fish to an animal which moves on its arms and hands. And we can see that it has all of the structures that we need for motion on the land. The other thing about it is, and this is critical, it has a neck. Unlike all fish, if a fish wants to look in a different direction, its entire body has to move. With this particular animal, it has a neck. It can only lift its head up, it can move it side to side, and it has a certain amount of rotation. Now, it doesn't have the full range that we do. No. You had to start somewhere, but the ability to independently move the head up and down allows it to go in the shallows of the water, lift its head up, see what's going on, go back down. It also allows it to graze and to grab food side to side and lift it up. And we can see that the shoulder is separated from the skull. It creates a little neck here. And the beautiful flat head allows it to move around and has all the necessary things for a land animal. So we have this ability. It can move independently and move fairly well. It has the ability to look around and seek food. It has eyes on the top of its head. Oh, wow, this is the intermediate. And so we all begin to say that the Tiktaalik is really the fish. We see the round head with the eyes on the side and the basic fins. Oh, my connection is unstable. Come on back. Come on. There we go. It keeps telling me I have an unstable equilibrium here. And unstable, yes. This Tiktaalik with its flat head, its eyes on top, with a neck, specialized fin and ribs. It doesn't point this out, but it has a lovely, lovely pelvis to the actual theropods. Now we're back to our plant. Basically a flat head, eyes on top, with the ability to have the limbs that you can put underneath it, and the smaller pelvis here has now become a really large, big pelvis. So the rear legs can push and the front legs guide. So basically, why do we all have the same skeleton? We all descend from Tiktaalik, or something which is so close to this that we can't tell the difference. This is Tiktaalik rosea, which would be grandfather or grandmother, and this would be about 375 million years ago. Now, for your edification, I highly recommend Neil Shubin's book, Your Inner Fish, Journey into the 3.5 billion year history of the human body. I do not know if this is still in publication. As you can see, there is an ASIN number from Amazon. This is a penguin. from January of 2009. I don't know if it's downloadable at this point. It might be.
Yes, it's certainly still available to download, and you can also buy a physical copy according to Amazon. I checked that
Also, if you go onto the internet and look things up, especially in Google Scholar, and look up Tiktaalik, you will find dozens and dozens and dozens of publications out there. Original publications which discuss all this stuff in detail, and they're in the form of PDFs. You don't have to belong to the society necessarily. You can download a PDF and read the entire thing. So you're in a fish here, Shubin, Deschler, and Jenkins. This is the nature, the pelvic girdle and fin of Tiktaalik. So a major discussion on that. The cranial endoskeleton of Tiktaalik, and this just goes on and on and on. So the point that they are making is, this appears to be the intermediate species between we're in the sea, we're on the land. And so the answer to the question is, why do we all have the same skeleton? Because we all descend from the same animal, Tiktaalik. So I'm going to stop sharing and come back to life. Am I back?
You are.
Hi, everybody. So I now turn all of this over to the actual real expert in this field, Abby Hafer. And please, Abby, take it away.
Well, there were a few things that I was thinking about as you were talking. Just the other day, somebody who is an engineer was saying, well, you know, if we were to design the human body better, what would it look like? And he was kind of interested in doing this, you know, just kind of as a thought project and so on. And so one of the things that I pointed out to him is what you were just saying, that basically we have the tetrapod body plan because we're stuck with it. And so if you were just going to completely redesign humans, and you still want, you know, good sized brains, and you want hands and the things that make humans special, and you still want to work with, you know, bone and muscle rather than, you know, metal parts of the, you know, real robots, what would you do? And one of the things I pointed out to him is that if you were really just starting, you know, with a whiteboard of what would you want if you could start from scratch, there's no reason that we would have to have just the two body segments that we have, head and torso and, you know, forelimbs and a tail. We could have a few more the way that some arthropods do. Oh, and as a quick aside, we make a great deal of the tetrapod sea to land transition, but actually arthropods beat us to land by a long, long time.
Right.
They were already walking around on Earth when we were still swimming. So, you know, insects of various different kinds were already walking around. Hey, they provided a food source for us, so we like them. But anyway, but as I said, this does point out that other body plans are possible. Arthropods have all kinds of different body segment arrangements. Arachnids have two like us, insects have three, as you probably know. You get into centipedes and millipedes, and you know, you can have lots of body segments. But there's also no particular reason why we could not have more limbs. So for instance, if you wanted to solve the basic giving birth problem that we have of having very large heads on the one hand, but on the other hand, a bipedal walking arrangement, which does allow us to have hands. If we could add an extra pair of limbs, we could walk on four legs and have hands, and that would reduce the need for narrow hips, because narrow hips are really important for bipedal walking. And so this is the problem that human beings have in giving birth, is that on the one hand, a female who wants to give birth has to have wide enough hips that the birth canal can be wide enough that the large-headed baby can get through it. But on the other hand, the hips have to be narrow enough that walking on 2 legs really makes sense at all. But as I said, no reason why we couldn't walk on 4 legs if we were totally designing things from scratch. So this really is, like, to my way of thinking, one of the best pieces of evidence for evolution is that, just as you pointed out at the beginning, and that was a beautiful array of skeletons and creatures, man, you get onto land and, you know, ignoring arthropods for a moment, all the vertebrates have the same layout. It's the tetrapod body plan, and as I said, we're stuck with it. And, you know, maybe we'd be better off if we could have some extra limbs or a few other things like that, but we didn't get that because that's not what Tiktaalik had. So,
I think you just said arthropods twice. What are arthropods?
that is the big phylum that includes insects and arachnids and lobsters and all, basically things with hard shells.
Okay.
Basically, I think that one of the things we have to remember is, why did Tiktaalik come out of the water in the first place? Well, there was food there. There were all these marvelous insects just sort of wandering around that were food sources. There were plants of all kinds that were just available. And, you know, that's one of the things that tetrapods do. We eat, and we're good at it.
Maybe they
Right.
were escaping predators in the sea.
I was about to say, that's another thing. You look at Tiktaalik's body plan, and what it looks like is a shallow water creature. And shallow water creatures do have this thing where if there are predators in the water, they walk on land. If there's predators on the land, they go into the water. And likewise, the food sources. But sometimes it seems almost particularly predator avoidance is something they do very well by deciding to be either in water or on land, depending upon what seems most useful at the time.
I guess the birds decided to fly to get away from predators on the land, right?
That's right. Yes, exactly. And you have things like flying fish that exit the water if only briefly. But it's the same concept exactly. And in fact, yes, Joanne was pointing out that in one of my other talks, and I was looking around on the laptop that I'm on now, and sadly I could not find that picture I have of a fish climbing a tree. We have fish today that occupy that sort of shallow water niche and walk in and out of the water to their heart's content. And as Michael was saying, you know, as if walking up on land wasn't enough, sometimes they will actually walk up into trees in order to get away from still other predators. So fish can be pretty creative.
Are those Abby, are those mud skippers?
Yeah, mud skippers. There's a bunch of different species of mud skippers. They're really fun creatures. They, like amphibians, can breathe through their moist skin. Though they also have what are sort of functionally primitive lungs. They're called opercules, but it amounts to sort of pouches in their cheeks that have lots of blood vessels in them. And so they more or less go, and that forces air into the blood vessels. And it's kind of like having a very primitive lung, except that it's not a lung. But anyway, so yeah, mud skippers have all kinds of really creative adaptations.
Didn't our ancestors do the opposite? Because we were in the trees and then we came down from the trees and tried to walk upright and run around.
Well, I had an old botany professor who said that with evolution, you never get to go back, but you keep making more trips around the barn. And so, yeah, you know, our ancestors went from the sea to the land to the trees to back to the land, and you know, yeah, that's us.
And the sea mammals descended from land creatures? I mean, the dolphins.
Oh yes.
Yes.
Oh yeah, they're very clearly descended from land creatures, and have some nice looking hips that at this point are, you know, very vestigial, but nonetheless clearly there. They have hair, not much, but you know, a few little hair follicles here and there and this kind of thing. And I'm not just talking about seals that obviously have hair. I'm talking about whales. Other
Interesting
things that I was
It's interesting to
thinking,
look back at the number of people who have looked at the history of whales and where they came from and the original animals that they were on the land that decided to let's take a swim. And the more they swam, the more and the long evolution of the whales. It's a most marvelous study.
yeah, whales are cool, and we keep finding out more about their sort of deep history. But the thing that's kind of fun about the land to sea transition is that you can see lots of intermediates as well. You know, you see seals that, you know, have limbs and use them and this kind of thing. And then, or sea lions in particular, that are pretty good at sort of oomping around. And then you'll have other types of seals that are pretty bullet shaped, but not quite entirely dependent upon being in water, you know. And then you wind up with things like dolphins and whales that utterly do not have limbs and have to stay in the water. But what I was going to say is another thing that's fun to look at is that if you look at a lot of shallow water fish, or actually I should even just say bottom dwelling fish, although there are some bottom dwelling fish that are like flounder and they're just flat along the bottom. There are other bottom dwelling fish that essentially have little legs that they walk around on, and they don't necessarily have to bear a great deal of weight because they're in the water, but nonetheless they're not just like shuffling along, they're kind of running along, sometimes even on two legs, you know, which are present and extant today. There was one time when I had fun, I think I just Googled the words fish feet, and I came across all kinds of fun videos of, as I said, bottom dwelling fish that have all kinds of different arrangements, because sometimes swimming is not actually the most efficient arrangement if you're near for getting around, if you're near the bottom anyway.
Abby, I have a question for you. One of the things Joanne pointed out in her slides was that Tiktaalik had sort of 5 digits, 5 phalanges, and I think she showed whether it was Eusthenoptera. Let's see, what was that called? Eusthenoptran, the sort of more fish-like organism that came before. And when Joanne was showing that, she showed sort of 5 rays, 5 different spines in the fin. These fish feet that you're talking about now, did you find fish that, you know, plodded along on the bottom of oceans and whatnot that had more than 5 digits or 5 rays in their fins? Is 5 just a happenstance?
I wouldn't be able to tell you about these videos because they are just videos of actual live fish kind of, you know, doing their little thing. And who knows what particular fin wound up being the thing that became adapted for moving along the bottom. And they very likely are not the same fins at all. So the answer there is I don't know. But another thing that I loved about Joanne's presentation was not so much the 5, which I suspect is just kind of an interesting evolutionary happenstance, but, you know, as you put it, what is it, the 1 too many 5. The 2, I thought that was really interesting because, yes, obviously we see that in all vertebrates, is you see the 2 bones in what is our forearm, but that does allow for rotational motion. You know, if you hold these 2 bones still, see, I'm grasping my wrist here, my hand can't rotate. The ability to pronate, as it is known, that is to say to do this, is entirely because we have the 2 bones here, one of which has a twisting association with the bone here, with the humerus. So it does this very nicely, and it basically flips the thumb up or flips the thumb down, and the palm goes with it. And that was something I hadn't thought about before with Tiktaalik, was that not only did it have those 2 front limbs that could push itself up and had the strength to do it, but if you were going to do this, it's hard doing, but this kind of a motion, kind of the old crocodile walking on land thing, you'd have to have a certain amount of rotational ability in the hand to be able to do, or, in this area, you'd have to be able to do a little bit of this in order to make that work. And I hadn't thought of that before, but yeah, that really worked for getting us up out of the water, being able to do a little bit of this.
So our leg bones with the what are the two bones in the leg, the tibia and the fibula?
Right.
We don't do so much in terms of dexterous movements with our legs. I guess we can twist our foot from side to side.
Yeah, you can twist your foot from side to side.
Let me tell you, as somebody who had a broken ankle last
Okay.
year, you definitely notice it when you can't do that.
Huh.
To me, there's one puzzle about the 5 is why it is so conserved, but it's not perfectly conserved, because there are hexadactyl cats, and there are even hexadactyl human beings. My grandfather was one. So why is that so conserved?
Well, a lot of frogs tend to have 4 fingers. If you ever see a lot of tree frogs, they do those 4-fingered things.
But let me talk about another puzzle.
Sure.
We were talking about how this all got frozen 375 million years ago. All these anatomical details, with minor variations, got frozen 375 million years ago. But why did they freeze then? You go back another 200 million years, you don't even have creatures with bones. What happened?
Well, this is just in our line of descent. I mean, there were so many other, crabs, spiders, all these other, I don't know what the technical word is. It's just our particular line of descent.
It froze too. You go back to the Cambrian, and most of the modern body plans are there. You go back another 50 million years and they're not.
Right, although I loved what Joanne pointed out, which is that modern fish are also really different from those old fish, or at least from Tiktaalik, which is why people have a very hard time imagining the sea to land transition when they look at, a bass. But as I said, that's because modern fish are also the result of the past 375 million years of evolution. So they've done a few things since then too.
Why in the water were they free to make these skeletal innovations, and we on land were not?
Well, there's been a lot of diversity. It's just that the basic numbers, like 1, 2, many 5, that's the pattern. But otherwise, so the topology is continuous, but the structure's changed a lot.
Why do so many vertebrates have tails? It seems like,
It's the end of the spinal column.
But why not? It doesn't seem terribly functional in a lot of them to not just have a little bitty thing there like a frog or a human.
You're sitting on a branch of a tree, the tail is very handy for balancing, right?
And for running too. If you run on all 4s, having a counterbalance behind you is also helpful.
Yeah, watch a cheetah going at 80 miles an hour,
and the tail breaks off, and the lizard runs away. He doesn't have any trouble at all.
Grows another one.
But look at a cheetah when it's hunting, and it's taking these marvelous turns. It's the tail that counterbalances as it's going along, 60 miles an hour. And again, a dog, look at a regular dog running around, and look at this motion of its tail relative to its body. It's very important for balance of the back end, which is way back there. The head's up here, but you got way back there. And so those creatures with great tails like that do extremely well. Now, it's not saying that all animals have nice long tails. Bears don't. We don't. Chickens have a very modest tail until you get to things like peacocks and things like that.
And that's not a tail
frogs have
anyway.
none.
So
Yeah, it really isn't a tail. And frogs don't have any, but lizards do. Now, why did the amphibian have it, but then the lizard doesn't have it? Well, maybe it went through that newt salamander kind of arrangement. I
I
don't
was
know.
going to say, newts and salamanders are amphibians, and they definitely have tails. Now, I mean, things like squirrels, it's like a tightrope walker's staff that they use for balancing. That's what the squirrel's tail is about.
They're marvelous athletes.
Right.
One of the, when I lived in Colorado, there was a Steller's jay. I used to call these things interstellar jays because they're huge. And there was a Steller's jay that came around our house who was completely lacking tail feathers. And I had learned that they needed tail feathers in order to steer and fly, but this guy had no trouble at all. So I'm not sure.
Well, I've got a question now. I mean, was he a regular, like at your bird feeder or anything like that?
Yes.
Okay?
Did he eventually grow a tail
I
back?
talked to Joanne. She decided.
Not that I saw. I didn't see any
come over today.
intermediate stage. I mean, they
I
come
told her
and
that he
go.
was
and-
Yeah,
looking to see
right.
them, and
I
she said
understand
she
you
still
probably
wanted to
didn't
stay
have him
home.
tagged or anything like that,
No,
but the point
no.
is birds can do a fright molt. So basically, if a predator is grabbing for them and grabs their tail feathers, like a lizard, they'll just let go of the feathers and that way they get away. And in fact, a lot of times if you just frighten a bird, you'll see a few feathers fly off.
Yeah.
All the feathers are a little bit looser when they're afraid. So as I said, it may just be that guy was being pursued by something that had his tail and he did a fright molt and, lost his tail feathers for a while.
Yeah.
Well,
Isn't it
and
true for humans as
The
well?
thing was that it didn't seem to bother him in terms of his ability to fly, and I had always thought that the tail feathers were steering devices.
Well, it may be that it's easier to fly that way, but you can
Maybe.
manage it without, Kind of
And
like
Even-
being
even
without a
humans,
gallbladder. They really are useful, but we can live without them if we have to.
Yeah, even humans can shed hairs when they're frightened, right? Sometimes. You heard of that?
I've heard of people shedding hair when they have periods of stress, certainly. I didn't
Yeah,
know about
okay.
the sort of more instantaneous fright.
Yeah.
But,
But
yeah.
can I change the subject to DNA now? Because this ancient fish coelacanth, which still survives, I mean, presumably we have genome that's DNA and we understand its relation to other fish and somehow. Of course, Tiktaalik is only fossil, so I guess there's no possibility of getting any DNA from Tiktaalik, right?
To the best of my knowledge, those are all minerals.
Just minerals now. Yeah.
375 million years is a long time ago.
Yeah.
maybe if
We
we,
need to find a Tiktaalik that's frozen in the permafrost or something, and
Or
then
ma-
we can clone it, right?
or trapped in amber, maybe. The,
Yeah.
7 feet long.
Be a
trapped in
big piece
amber.
of amber,
Yeah.
yes.
One of the things that came to mind when you were talking about the skeletal features in Neil Shubin's book, he spends quite a bit of time talking about the head bones as well. So it's not just the limb bones, but also you can look at a fish and discern that several of the cranial bones have been repurposed in land animals for ear bones. So some bones that are relatively large in the cranial outfitting of a fish skull and a fish head, some of those bones have shrunk to tiny size and are used, for example, as the stirrup and anvil and some of those tiny bones in our ear. They're still preserved, but they're completely changed in function. But the number of bones has remained constant.
Huh, that's interesting.
Why was it preserved over 375 million years is a wonderful question. And what it does say, to me at least, is that it's extremely functional, that it works. If it didn't work, it would go away. And we see, for instance, some variations in the dinosaurs, especially the theropods, and we see the same thing in chickens, where they're now down to 3. And that vestigial thumb and baby finger are really very hard to find. You still find the thumb, but the baby finger is almost gone. And so we're seeing over the course of 375 million years a lot of variance in the structure of the hand, feet, but the structure of the overall upper and lower arm, the legs, the basic body shape, it's functional. It works. It really works extremely well for a land animal.
Well,
and even for a flying animal.
And I think that's why, for instance, when I was talking about extra limbs, 4 is a good stable arrangement. If we had 3, it would just be pretty awkward. Whereas, locomoting on 4 limbs is pretty good for balance on land, and on land is where balance really starts mattering. And 2 works pretty well that way as well. Or you can cheat and be a kangaroo and use 3.
Well, look at our vehicles. Vehicles have 4 points of contact.
Right.
The most stable vehicles.
Well, actually, like chairs have 4 legs usually.
Right.
3 is more stable because when
That's
you've
true.
got 4, one's usually not touching the ground. Right.
True. But if you're talking about locomotion rather than just staying in one place, 4 limbs actually works pretty darn well. As Joanne was saying, it's a very functional arrangement. So there was not a great deal of evolutionary pressure to have more, in favor of more limbs, for instance.
But note that the most successful land animals have 6.
Yep.
What?
Insects.
They're far earlier than us, and they're a completely different group of people. As Abby has pointed out, these are arthropods, and arthropods were on the land for at least 50 million years longer than any of us, and possibly as much as 100 million years. If you go back into the period of the Carboniferous, where the forests were growing and everything else, just after Snowball Earth, you've got huge numbers of plants finally beginning to get on the land. And the first animals that ever take the hold of the land are the arthropods. And long before we came out of the ocean, there were dragonflies, there were flies, there were all sorts of, not necessarily mosquitoes, but there were flies and dragonflies. And the dragonflies were 3 feet across.
Yeah.
These were big critters. And there were.
I'm not disputing that. I'm just pointing out that
we're latecomers.
The supposed advantage of 4 limbs may not really be true.
Well, as I said, as Joanne said, it's a good functional arrangement, but other arrangements work as well.
Like with fingers, digits on the hand. I mean, I can see that 3 is much better than 2 because for grasping, and even 4 would be good. The advantage of 5 over 4 is not quite obvious, but you wouldn't have. But why go for 6 or 7 when 5 is plenty? So.
I have to talk with my cats about that. I had several cats that had 6 and 2 that had 7 fingers, and they were just marvelously useful all the time.
Well, part of it is
playing the piano. I mean, it'd be a great concert pianist, right, with 6 or 7 fingers on each hand.
Of course, bang, bang, bang.
It's a balancing act.
Digital arithmetic is counting in tens because we have 5 fingers on each hand, right? If we had 4, we'd use octal arithmetic.
Right. You're right. There's a balancing act between. It's almost an economic.
Isn't that what Tom Lehrer said? Base 8 is just like base 10 if you're missing 2 fingers.
Right.
Exactly.
It's kind of an economic question too, because you can use ideas out of economics about efficiency and cost benefit to help understand that maybe 30 fingers per hand would have been fantastic. The ability to manipulate many tools at once with your hands, etc. But at some point, it comes down to the cost entailed in developing, maintaining, physiologically engineering, as it were, some of those complexities versus the amount of material.
30 fingers, it would be very dangerous to use a hammer.
Oh, yes.
Yes.
Yeah, along these lines, you sometimes see comic pictures of aliens from other planets with 3 eyes, and they're sometimes in line, which is stupid because the middle eye gives no information. If you had 3 eyes, there'd be in a triangle because then you get extra information.
Yep.
Well, if you want to talk about eyes, this really is where our non-tetrapod relatives have it all over us. If you look at spiders, I mean, they got just like eyes everywhere. Um, horseshoe crabs. Now they have an amazing bunch of eyes, all different kinds of eyes, like all over their bodies. So as I said, two eyes is a good number. Um, if you have two eyes pointed out this way, then you actually have pretty nearly a panorama. You're quite right. If we had a third one pointing backwards, that would be handy. Then really nobody could sneak up behind you. By having two in the front, we actually get parallax vision. We get binocular vision so that we have depth perception. But as I said, many, not tetrapods, but many other animals have multiples of eyes in all different places.
Well, and then think about the digits. There are some animals that have evolved such that two of their fingers out of five, two of them are actually what they walk on.
Yeah.
So things.
Horse.
Yeah, horses.
Horse walks on one.
And the horse
and
walks
on
on
its
one.
fingernail.
Right.
Right.
So it's the same plan that's repurposed, like Abby was saying, and Joanne, is you take the basic architecture and you can play with it in infinite ways, but the basics remain. Dogs have 5 digits, but one of them typically is the dew claw, which is used for very little, maybe used for grasping prey, but in a wolf and whatnot. But they typically, dogs, if you look at the structure of their, especially their hind legs, they walk on their fingers, and like many animals do.
Well, and that also gives them another lever for locomotion. So they can do springing the way we can't do, as do cats. Because, instead of just having, as we have, sort of the lower leg and the upper leg, and we have a foot, but we don't really think of it in terms of using it a lot for springing because it's not that long. If you have a much longer foot, then it's a much better lever. And, you could have an amazing stride if you had really long feet that had, the appropriate musculature attached to it. This is actually what you see in artificial running feet now. People who have, who are amputees, who have had feet affixed to them for running. Here's another tetrapod coming to join me here. Anyway, they can leap, like this guy can leap a lot better than I can because he has that extra sort of relatively long foot to join a lever to, or as a lever, I should say.
Yeah.
So they can do a lot more that way. Now, there was something else you were talking about.
But still, the puzzle is, why did evolution spend 200 million years inventing new structures and then the next 375 just tweaking them and repurposing them and all that? What changed?
Once again, we as grand scientists come to the conclusion that we have no idea.
Well, maybe you can think of it partly as, when I've thought about and occasionally talked about the Cambrian explosion, for example, you can think about putting a liquid in some kind of container that's got holes in it, and the liquid that shoots out the holes is the liquid that propagates in space. Now, if you do something analogous with time, those holes are opportunities, they're niches, they're ecological niches. And originally you just get a mishmash, anything goes. But as soon as you've got a structure of predators with jaws and teeth, or you develop a necessity to moving quickly through the water to get away from predators, you start to have some physical, environmental, and ecological pressures, if you will, that help drive evolution towards certain locomotive and predatory efficiencies. So I think it's plausible that anything goes when nothing's after you and food's easy to find, but competition winnows that field down to streamlined fish bodies and efficient propulsion fins and whatnot. So part of it's probably, it sounds plausible and reasonable to me, that part of it is just imposing efficiencies and pressures for efficiency on a amorphous amalgam of expressions of ways to be a body plan.
I mean, isn't one of them, if not the most significant step in evolution, when it was only single cells for a billion years, and then two decided to stick together to their mutual advantage, and that was the beginning of multicellular life. That's when evolution really sort of moved on, because then you had more cells sticking together, and then they differentiated, and then you got the beginning of the tree of life in a sense. But for a billion years,
yeah, no, there was a lot that didn't happen for a long time. And body segmentation is another one of those big steps that then allows for a lot of other things to happen. But if you look at sea creatures, there you have much more of a proliferation of body plans. I mean, there's a lot of tetrapods, but we may be giving ourselves airs here. Other things that are on land with us are things like snails. That have a very different body plan. And as I said, if you look in the water, there's the whole arrangement of animals that don't even have bilateral symmetry, that have radial symmetry, jellies and all of those kinds of things, and sea urchins. So there are a lot of things that are possible. I do think that land maybe limits things a little bit because you've got to hold your body up against gravity or deal with gravity somehow. I mean, worms just kind of tunnel through the soil, but they have to deal with gravity in a way that, say, a nudibranch in the ocean just doesn't. And so, there are different, and if you're not going fast in the water, then you don't need a torpedo-shaped body. So you can have all kinds of interesting body plans if you are slow and weightless in the water. A lot is enabled that way.
One of the weirdest things I recently learned is that echinoderms like sea urchins are bilaterians.
Really?
Their larvae are bilateral.
Right.
And
Okay.
they fold themselves up usually into a pentagonal symmetry.
Oh, I did not know that. Okay.
But it's a very strange development process.
Well, that's interesting, John. You talk about,
and in fact, the DNA evidence suggests that of all the phyla, they are the closest relatives to us.
Yeah,
Echinoderms?
Yeah, most primitive sort of.
Well, they, we have a more recent common ancestor with echinoderms than we do with arthropods.
Right.
Example.
Yeah. Okay. Mm-hmm.
Yeah. One of the other thoughts that come to mind about that is what you mentioned about the fivefold. They fold themselves up into, fivefold symmetry, and there's that number 5 again. So there may be some, geometric or physical efficiency in having 5 appendages or fivefold symmetry that exhibits itself in surprising ways. Maybe a fivefold crystalline symmetry. It lies at the heart of the molecular plan for having 5 phalanges, for example.
There are no fivefold crystals. There are quasi-crystals, but there are no fivefold crystals.
Yeah, I was thinking that soccer balls and whatnot, you have to have a combination. Yeah.
I was going to suggest, you were talking earlier about why don't we have more multiples of digits. And again, this is the kind of thing where you do have to wait for the mutation. And as John has pointed out, they occasionally show up. In humans, you have 6-fingered humans sometimes. I've had cats with extra toes. And sometimes the extra toes in cats do wind up becoming essentially like a little colony of their own, where you'll have a whole lot of polydactyl cats. So clearly the extra toes do not seem to harm the cats.
Oh, polydactyl, hexadactyl cats are more dexterous with
And I had
grabbing
one, and
things and
oh, I had one, and I swear it had two thumbs, and
yeah,
it was
right.
very hand oriented. Um, so there is some advantage there, but clearly it's not something where it has been such an advantage that polydactyl cats, now rule the cat
Yeah.
world.
Yeah.
And likewise, 6 and 7 fingered humans have not completely overtaken 5 fingered humans. So clearly it's not that much of an advantage to us the way we are now. And
Well,
that's always the way it is with evolution, is that you don't get to plan ahead and think, man, in several million years, if I had 30 fingers, I could be a great concert pianist. You don't get to do that. You have to wait for the mutations in the first place. And in the second place, that mutation has to do you some good right now, such that you have more offspring than other people do. And so do your offspring and their offspring and their offspring. And that's why we don't have 30-fingered concert pianists.
And to quote George
Oh, thank
Orwell's
you.
Animal Farm, 4 legs good, 2 legs bad. 4
Right.
legs good.
Except for except for birds.
Yes.
And they had to work around that.
Right. Yeah.
One of the things that has always
Well,
amazed
yeah,
me about
there are
hands. Go ahead.
that there are also social things. My hexadactyl grandfather's parents had his extra digits surgically removed because it was not socially acceptable to be a hexadactyl human.
Held by gloves. Well, the other thing I was noticing with the human hands, we have evolved a really interesting set of skills. The hand is really divided into 3 segments. We've got these two, and this one. They can operate this way, they can operate this way, they can operate this way, and we can actually grab a bottle with these 2 fingers and twist the cap off. We got, so that's the full hand. If you had a bottle or something, you could grab the bottle with these and manipulate the bottle this way, or manipulate a can or anything. So you have multiple hand grips, but these 2 are grabbers and these 3 are manipulators. And depending upon the strength that you need, you can either use 3 or 2 in any combination. And so our hands have been adapting over the years to a multiple use and multiple skills. These fingers are becoming less and less useful, except for grabbing and holding, whereas these 3 continue to manipulate. And I wonder, over time, will these fingers gradually go so that we end up with 3 fingers? Or are we going to retain this marvelous skill that we have of 3 different sets of tools and 5 fingers?
Well, one thing that's been pointed out about our particular kind of opposable thumb, which is quite remarkable, is that it does allow 2 radically different grips, as John has been demonstrating with the hammer and the pen. There's the power grip like this.
2 pens as chopsticks.
Yeah. There's the power grip like this, which is actually very strong, and you can hold a hammer with it. You can do a lot with this. And then there's the fine grip like this. And this is the kind of thing that most other organisms' hands can't do. They don't have the combination of the fine and the power grip, which is quite remarkable. So yes, you can do.
I can hold on to the bottle,
and we can throw
the cap.
Right.
But we've been talking a lot about the hand and fingers, but not so much about the foot and the toes, which also are 5. We don't have opposable big toe. In fact,
no.
I guess some of our primate relatives do have and they use their feet and long toes a lot more for hanging onto branches and stuff like that. Right? Yeah.
Well, human feet are kind of odd in that from the ankle down, they're very compressed and wide, and that's got to be some adaptation to bipedality, because we're, as Abby pointed out, a cat has a much longer foot. The actual foot that the cat has is its fingers or its toes, whatever.
Right. What we think of as the cat's foot is just its toes, right? And you have this big long foot out behind the toes. Yeah.
Yeah. And most mammals I can think of anyway, and probably most vertebrates are like that, but our feet are different. But then again, how many bipedal mammals are there? There are plenty of bipedal birds, but they're a different they readapted the skeleton in completely different ways than we did. They got the same basic pieces, but they used the pieces in very different ways.
Mm-hmm. I would like to point out there's one thing actually I'm going to tell my students, since time is running out, and this is always a fun thing whenever you're looking at a skeleton or if you're looking at a bone. There are two things to look at. Basically, or one interesting thing to look at, and that is anytime that you see something sticking out from a bone. So, you have a bone and you have something sticking out from it or doing this or whatever. That'll tell you something about what that bone is used for, where there's a protrusion of some variety, and that can include a crest or something, actually sticking out more. It's generally either where it forms a joint with another bone, or it is providing a place for a muscle to grab on. And in physiology, surface area is a constant consideration. And so if you have a powerful muscle, it needs more surface area to grab onto a bone, or, when it contracted, it would just pull itself off the bone. So you need a lot of surface area for a powerful muscle to grab onto, which means that when you look at where bones stick out, first of all, figure out if it's forming a joint with another bone. If it's not, and you have something sticking out, it's usually because a muscle is grabbing on there. And that can tell you a lot about how that animal makes a living and how that animal locomotes. So for instance, if you look at our vertebrae, we have these spines sticking out the back. And, they're usually maybe about this long, roughly speaking, but that is where our posture muscles grab on so that we can actually stand up like this. But if you look at the spinous processes, as those processes are known, on a whale, they're huge because because they locomote with their tails, basically. They're doing this. Right. So as I said, you have big, huge spinous processes for those big, huge spine muscles in whales because that's how they get around. And in general, when you see something sticking out like that, that tells you where muscles are attaching. You were talking about birds was what made me think of it. If you look at a bird skeleton, the next time that you eat a chicken or a turkey or something like that, the breastbone here is our sternum here, and our sternum is flat. Whereas if you look at a bird's sternum, there's this huge process sticking out in front that's known as the keel. That's where the flying muscles attach. So as I said, anytime that you see something sticking out on a bone, it's a place for a joint or it's a place for a muscle, and that'll tell you a lot about how the animal makes its living.
So there's one mystery I'm aware of related to what you've said, Abby, and everything I've read completely agrees with your points. But there's one big mystery, and that is the human chin. The human chin juts out, and other primates and other mammals don't have a jutting chin, and even some of the hominid ancestors lack it. So there's a debate among people who study human evolution and human physiology, as I understand it. There's a debate about why is our chin prominent? Is it relevant to something like sexual selection? You know, we think that a strong chin is beautiful, you know, and so it's not it's not related to some physical activity, etc. So there is still some mystery about human physiology.
Oh, sure.
I have seen a recent hypothesis that
Sexual selection
connects
spurs
this to our wisdom teeth and the trouble we have with them. And that is that part of jaw development in our ape relatives seems to involve how hard they have to chew when they're growing. And the more they chew, the more the jaw grows.
Yeah, I've seen that.
And now we have, we cook our food and we grind up our grain, and we don't need to chew as hard as our ancestors did. But our physiology hasn't caught up yet. And so we have overbites, and we have wisdom tooth problems.
So you're saying it's vestigial, basically. We kind of have a vestigial chin.
Yeah.
Okay, it's a possibility.
And if we went back to the diets of 500,000 years ago, we might not have that kind of chin.
Well, certainly.
Only if women found chinless wonders more attractive than
Right.
good firm
Right.
chins, right?
Right, and then we also, you know, the musculature of the face and the jaw is much less robust on Homo sapiens than it is on some of our primate relatives, but for reasons that John explicated there about not needing to chew raw grains and whatnot.
If you compare our facial muscles with the Neanderthal,
Oh, right.
Neanderthal is very, very robust through the chin and the lower face, whereas we're sort of wimpy.
Yeah.
Right.
All right, well, we are out of time for today. Joanne, thank you for bringing us such a delightful topic. We've all, I believe I can speak for all of us, I certainly speak for myself, had a great time talking about it and learning about it. I hope that our viewers have had a similarly illuminating and fun time. We will be back in 2 weeks on July 24th to talk about more science, and we're doing the 7th and the 21st of August. We have a special program on the evening of Thursday, August 12th, where we will join the American Humanist Association for a special Sidewalk Science broadcast via their social media platform. So thank you all for joining us today. Thank you to those who are going to watch this later. You can always leave comments and questions in the YouTube video chat. Subscribe to us, give us a thumbs up, let us know what you think, and we will be back with more Sidewalk Science in just a couple weeks. Thanks, everybody.
Bye.
See ya.
Everybody, bye-bye.